Before I will start, I'll go ahead with our review. I need to tell you the most important 10 minutes summary of this course. This is to remember forever. Something is so simple, just to make it easy for you to remember what you have learned in this course. Just 5 points in 10 minutes. 1, 2, 3, 4, 5. Just 5 points. Very simple. The first one is a definition. What is the definition of thermodynamics? Thermodynamics is a science of energy and entropy. Science. So you remember forever. This is the definition of energy and entropy. Energy can be heat, can be work, can be even mass flow rate with energy added to the system. Entropy, S. For example, delta S is dq over T, which is a property of a system. We talk about this a lot, about the work, about Q, but this, remember, it's a science of energy and entropy. Something conservative, something is not conservative. Something cannot be neither created or destroyed, something always increases. This is the definition of thermodynamics, the main definition. Okay, guys? For the second one, always thermodynamics deal with thermal equilibriums. This is really, really important. What do you mean with thermal equilibrium? Something that had the same temperature throughout the system. In other words, we have, let's say, compressor. We have a turbine. We have any device, compressor. Flow going in, flow going out. This is has condition, this has condition. I don't care what happened in between. I do not care. Thermodynamics do not care. In between, something called, for example, thermomachinery. We have a stator, we have rotor. So we have a rotor, we have a stator, we have velocity triangle, we have design, we have off design, we have steady, unsteady, we have leveling design, NASA design, we have Carter design of the airfoil, of the blade, how the N affects the results, the velocity triangle in relative rotation speed. So all of these, we have another stator, and this is cascade. We don't care about all these details. For us, this is a black box. We see control volume, something going in, something going out. That's it. State 1 to state 2. This is called thermal equilibrium. We don't care about the transient or what happened in between. We care about is and was. Is, which is currently, was previously. That's it. 2 instances of thermal equilibriums. We have 2 ways to get data. The data here, 2 ways. We have either equation, like ideal gas law, and we have steam table. This is the 2 ways to find data. Regardless how we do it, but we have 2 ways. This is the reality. The reality is, I don't know, have you ever heard about, for example, machine learning, guys? Machine learning, anyone heard about this? Does anyone heard about machine learning?
Yes.
So when we have something can be written in an equation like this, that's good. Sometimes you cannot. Look at YouTube, for example. YouTube, when you open YouTube with your account, they give you recommendation. This recommendation based on your interest. Movies or actions or songs, slow, whatever the style you want, you find data. So this is called data. This data is discrete data. It's given in the tables. So when you have this data, for example, for us, it's a steam. You have pressure, you have temperature, you have volume, you have internal energy, enthalpy, entropy, and so on. These data are not given explicitly in an equation. So we have table. We have manipulation for that, like what we have learned here. So the whole point is you can have equation y equal 5x plus 3, or you have table x, y, z, and from x you can get y and z. That's called data. So this is the two ways we see data in our life. Machine learning try to get something in between, to find a model to fit this data, to represent it. So anyway, so the whole point is you can have either equation or tables, and it depends on the fluid medium. So thermodynamics, these 3, 4, 5 things. Definition, which is science of energy and entropy. We deal with only thermal equilibrium systems. Data can be ideal gas or steam. That's it. So simple. For the fourth thing, we call about delta T. This is so important. In thermodynamics, our driver is delta T. Our driver is delta T. Let's take an example. You know, I think some of you heard about the fluid mechanics, regardless if you took it or not, even in high school. In fluid mechanics, if you have flow in a pipe, what is the driver, guys? Why the flow move from this point to this point? From inlet to exit, why? Does anyone know why the flow driven in a pipe or tube in fluid mechanics? Due to what? So due to pressure gradient, delta P, or delta P over X. So pressure here, higher than here. Let's see, here is 100, here is 80. So the flow will driven from high pressure to low pressure. This is always. So for fluid mechanics, the pressure is the driver for the fluid. In thermodynamics, the change of states, the delta T is the driver. So I'll ask you a question, guys. If you put your hand, don't do that, but if you have your hand and you touch something is hot, let's say your hand is 37 degrees and you touch something, let's say 150, 137 degrees. If you touch something like that, this is your hand, and you touch something like that. This is because if it has 100-degree extra, it may burn your hand, correct? It may burn your skin. So what will happen if you have touched it with something, let's say, minus 63, which is again negative 100 degrees. So what will happen? The same thing happen. So if you put your hand in something so cold, like minus 100 degree or 200 degrees, your hand will burn exactly same as if you put it in something so hot. So delta T from hot to cold to hot reduce flow of a change. Thermodynamics, flow, change in temperature or energy, and change. This is so important. I'll give you an example. You know, guys, the homeless people, you know the homeless people? If you could check them, you will see the tip of their, for example, fingers or even toes, little bit black. Why? Because this is the very far part of the body. It has very minimum amount of blood, very cold, exposed to cold atmosphere, cold ambient. That's why it's so black, because it's mostly burned. The skin of the tip fingers of the homeless people usually black, because it's burned due to delta T, because it's exposed to negative temperature sometimes. So continuously exposed to negative temperature, and their body is 37, that's to create about 50 degrees temperature difference. It burns the skin. Okay, guys? So definition, science of energy and entropy, deal with thermal equilibrium. We have two types or categories of data, either equation or table. This is thermodynamics, or even life. Delta T is the driver of the information, change for states from one to another. Positive or negative always cause the same effect. If you put your hand in something hot, you will burn. Something so cold, you will burn. For example, the last but not least, it is the Ferris law. We have two first laws: closed system and open system. Closed is Q minus W equals delta U. This is the very general one. Q minus W, sorry, equal delta H. This is a very simplified by neglecting the kinetic energy and potential energy. So for closed system, Q minus W equal delta U. That's always correct. Flow in a tank, piston cylinder like Otto cycle, Rankine cycle, diesel cycle, dual cycles, Ericsson. So Q minus W equal delta U. Can you see that, guys? Q minus W equal delta U. Q minus W equal delta H. Let's make it H. So this is open system, this is closed system. We have two systems: closed, no mass crosses the system; open, mass crosses the system. So heat minus W equal internal and change in internal energy. That's called first law of thermodynamics for closed system. Just remember this. I'll give you an example. You know, guys, if you are talking about mechanics, like mechanical engineer or even solid mechanics, if I said F equal MA, any one of you understand this? Does anyone of you do not do this? If this is the case, you can go to any other school. Now, F equal MA. What is this, guys? F equal MA.
Force.
Equal mass times acceleration. Definition of force. Newton's second law. If any one of you interested in classical mechanics, and he go, Isaac Newton is the father of classical mechanics. He said F equal ma, or force is a rate of change of momentum. Momentum, mass times velocity. Assume mass is constant, so mass times acceleration. It's always correct. We have hundreds of equations from this equation. This is Newton, the same as Navier-Stokes, the same as Maxwell equation, the same as, I don't know, like any kind of equation. It has a change. This is correct. Force equal mass times acceleration, which is the dynamics of a system. This is called classical mechanics. We have heard it many times from high school till this date. For thermodynamics, Q minus W equal delta U, Q minus W equal delta H. So if you remember this because you know classical mechanics, you need to remember this because you know thermodynamics. So these 5 key topics or points need to be always in your mind when you hear the word thermodynamics. Do you have any question, guys, in these 5 points? Do you have any question about these 5 points, guys?
No.
I wish that helps you to remember thermodynamics for a long time, very long time. I don't care about details. I do not mention too much equation here, I believe, except Q minus W equal delta U, which is, I believe, so simple. We have mentioned that many times. But anyway, this is the very, very brief of this course. What you should remember as a mechanical engineer or an engineer generally. I think most of you are mechanical engineers. I think so. Review 3. First of all, you need to have review 1, which covers lecture 1, 2, 3, 4, and a little bit on 5. Chapter 1 to 4. One through 4. So in a summary, we have a state. We need all the information. 2 independent intensive properties, 2 independent intensive property, independent of the size. They can get everything of this. You have either steam table, you have ideal gas law. For a steam table, it depends on the state. It can be compressed liquid, like compressor, pump, liquid. You have saturated mixture. You have superheated vapor. This is the steam table. So you need to have how to access the table. A4, table A4, A5, and A6 or A7 for water. For refrigerant 134A, we have table A11. So for example, refrigerant 134A, we have table A11 through A13. Ideal gas law, just PV equal RT. They're very, very simplified form. Pressure, specific volume, gas constant, T. The gas constant from table or just Cp minus Cv. And we can say delta U equals Cv delta T. Delta H, Cp delta T. The same for delta S. If you want S, here S is easy. It's a column, extra column in the data. But delta S is Cv ln T2 over T1 plus R ln V2 minus V1 over V1. The same for Cp ln T2 over T1 minus R ln P2 over P1. These are the ways, if you have two independent, any two, let's say pressure and temperature, usually like this, you can get the volume. You can go here and get delta U between two states, delta H, delta S. If it's isentropic, actually, if it's isentropic, you can just use this equation. If you have V2 over V1, you can use get T2, or just P2 over P1 equal T2 over T1 to the power K over K minus 1. And K is Cp over Cv. So the specific heat ratio, and this is specific heat difference, gas constant. And we have table for them. Table A to A, room temperature, A to B, average or distribution, A to C, we have function. So in reality, this equation was originally integration Cv delta T. Here from T1 to T2 and so on. Cv is function of temperature, which is table A to C. That's quick summary of chapter 1 to 3. Then we talk about chapter 4, first of thermodynamics, closed system. Just Q minus W equal delta U. And we hold it like this because we're going to use it a lot in the gas power cycles like Otto, diesel, and Dewey cycles. And we have other cycles like Ericsson, I think Edicton. I have a lot of cycles to use the closed system, first law of thermodynamics. Okay. For review 2, review 1, it has this. Review 2, we start from chapter 5. We ended by chapter 7. 6 was first law of thermodynamics for open system. 7 was the entropy, actually to 8, I think. 5, 6, 7. Okay, 5, 6, 7. 5, 6, and 7. 5 was first law of thermodynamics open system. 6 was second law, like statement by Kelvin Planck. Second law of thermodynamics. 7 was entropy. How we calculate entropy. For example, delta S, which is originally dq over T, can have 4 special cases. If temperature is constant, what is this, guys? Delta S equal to what?
0.
No, Q over T constant. Temperature constant can be taken out, so just delta Q over T, which is happen usually for
Isothermal?
No, happen for thermal reservoir, not thermal equilibrium reservoir. It means surrounding. So surrounding, you dump heat, but temperature does not change. So not isothermal, it's called isothermal reservoir or like surrounding. For example, if you have a system and you heat the system, let's say give Q, the temperature of outside does not change, 25, it's always 25. Change it to Kelvin. If whatever Q gave or take, this temperature does not change. So the entropy change of the surrounding, just Q over T 25, equal 25, plus 273 to make it in Kelvin, absolute temperature. So this is a delta S. Delta S for the liquid and solid. Does anyone remember? For liquid and solid, delta S equal to what? Solid and liquid? Anyone remember delta S for solid and liquid? Hey guys, no.
Specific ln over T, parentheses T2 over T1.
Exactly. What's your name?
Ethan, Sheila.
No. If anyone took bonus before, wait for the end of the others. I will ask 2 times. The first time, if you have already a bonus, do not talk. So if you do not have, go ahead and talk. If no one is talking, I will ask again for the other group who already took before, okay? So Ethan, you already have one. So let's go with delta S. Next, it's CV ln T2 over T1. For example, what is the Q here? Does anyone remember for the solid and liquid what the Q is? The heat given in this system, like water, warmed from 30 to 70. It has one formula, Q. It's a constant volume. So if you apply this equation, this of course is 0. So what is Q is? Does anyone remember?
Delta U.
No, it's MC delta T, not delta U, MC delta T. Heat capacity for liquid and solid is constant. There is no CP, there is no CV, just one C, like water. If I want to heat up water from 30 degrees to 70 degrees, say this. So C, 4,200 for joule per kilogram Kelvin for water. The mass of the water, let's say you make coffee for yourself, delta T, 70 minus 30. So you can get how much heat needed for this water, just pure water. And only pure liquid. It's not steam, it's not vapor and liquid. The same for solid. If you have a bar of metal, let's say aluminium. Aluminium has heat capacity, I think it was 912. So 912 joule per kilogram Kelvin multiplied by mass of the aluminium, delta T. Let's say you hide it from 30 to 100, 200, as long as it's not below the melting temperature and it is within the solid state phase, it is always MC delta T, always, for these materials. Then we took 2 equations, 2 things. One for ideal gas and one for steam table. For ideal gas, this is equation, 2 equations. I need to know from where we derive them, the T delta S, or how to change from them to isentropic. So we started from T delta S. Actually, we proved this, and we proved those. And we prove also this. So this one, give this one, like in the exam. Steam tables, we have additional column added to our system, which is entropy column, joule per kilogram Kelvin. It's per unit Kelvin. It represents how much mess you have. So this is a summary of chapter 7, and even second law we have like the Bent diagram, first law, Q minus W plus energy in minus energy out equal a change in the system for open system. So please go ahead and listen to review 1 and 2. I don't want to repeat the details, but I just go through the summaries. Okay, now let's go now with review 3. We have chapter 8 and chapter 9 and chapter 10. 3 chapters. Let's start with 9. 8, we have 3 definitions. Only 3 definitions. The first one, which is exergy, which is useful work or work per unit mass. We have irreversibility, which is useful minus non-useful. And we have second law efficiency, which is eta real over eta ideal, always less than 1, or it's 1 if it's a system is ideal. So for the first one, we said how much useful work. So if a system, it behaves as it is with some losses. So the network, like let's say you have 2 systems, 2 high. This is, let's say, power plant, and this is T low. So let's say you have Q high, and you have work, and you have Q low. There are 2 options here. Oops. Q low. We have here, this can be real or ideal, like Carnot cycle. The most ideal or most efficient cycle. See, this power plant, we have the same heat. This one the same as this one. So what happened here? In reality, we have more losses. We have more Q low. Q low is larger. We have more loss. Or the W net is less. So in reality, we get less work. This we call this useful. This is called useful work. We wish to be larger. We wish to be larger. Irreversible is the difference between the maximum you can get minus the minimum. Like for example, compressor. W actual minus W real. Because W actual is bigger because we need to pay less minus W ideal for compressor. This is I compressor. The same for turbine, but opposite. If the talk about system or even component, the second low efficiency is eta real over eta ideal. For example, eta real here, 1 minus Q low over Q. It was actually 1 W net over Q high, output over input. Here, just 1 minus T low over T high. This is real, this is ideal. Both of them are thermal efficiency. Okay, guys, this is summary of chapter 8. Chapter 8 will be in a problem. For example, if you are solving a power plant, if you are solving Carnot cycle, I can ask you for second law efficiency, if it's ideal or not. I can ask you for any other system. So it will be implicitly part of a problem in the very end to ask you, give me a reversibility of this problem, of this case. Chapter 9, this is important, which is gas power cycle. Gas power cycle, gas. It's a cycle, start from 1, end by 1. It's called cycle. This cycle, I'm gonna post a video today. We have in chapter 9, four processes for everyone. Can somebody tell me what these are, except not Ethan? So what's the first one, guys? From 1 to 2, 2 to 3, 3 to 4, 4 to 1. All of them, including Rankine cycle. What's the first one?
Compression.
Exactly. What's your name?
Lisbeth Sanchez.
What's your name?
Lisbeth Sanchez.
Oh, Elizabeth. Okay.
Yeah.
Okay. So you said compression. What's the next? Compression. What next? What's next?
Is somebody else?
Yes. Go ahead. Anyone?
Constant volume.
No. What's generally?
Combustion.
All the cycles.
Heat addition.
Heat addition. Perfect. What's your name?
Nolan.
Spell it, please.
Nolan.
Again.
Nolan.
Nolen.
An.
An. Okay. So the next one for all of them.
Expansion.
Expansion. What's your name?
Sean Johnson.
Does anyone also Johnson, or do you have last name, or this is last name?
Last name Johnson. First name Sean. S-E-A-N.
S-E-A-E-N. Okay. Okay. Gotcha. So the last one.
Heat
Anybody
rejection.
else? What?
Heat rejection.
Heat rejection. Perfect. What's your name?
First, Ramirez.
Ramirez? Yeah, I know. Yeah. Okay. Ramirez. So for all these cases, guys, all the designs, Otto, Diesel, Brighton, Rankine, all of them, we have compression, heat addition, expansion, maybe different system or even cycle, but these are the four procedure or 4 steps for all of them. Let's talk about the first one. We have either PV diagram or TV diagram. Otto, we have Diesel, and we have, let's say, Dewell. And of course, before them, we have Carnot, the 9.1, 9.2. So let's start with the cycle, and we have the PV, and we have TS, and if you want to get the ideal efficiency. Let's talk about the cycle. Here we have a piston that's exactly like car, as you remember, and we have here spark plug, and we have exhaust. The piston is going up and down in this cylinder. So this system, guys, it's open or closed? Spark.
It's open, but we assume it's closed.
Yeah. Who is this?
Ethan.
Ethan, I said to you, wait. I know you know, wait. So let's give first other chance. Then if they don't know, I'm gonna ask the people who talk already great. Ethan, Elizabeth, Noel, Johnson, and Ramirez. So these guys need to wait until the first, if anyone else get his chance. Some people a little bit fast, some people a little bit take their time. Let them take their time. You need to be fair. So we have here piston cylinder. It's originally open, but we assume it's closed to be able to handle it. So what's the first law of thermodynamics for the closed system, guys? Does anyone know from other than these five? First law?
Q minus W equals delta U.
Exactly. What is U again? What is U? For you?
Internal energy. Oh,
exactly.
I mean.
Yeah, internal energy. What's your name?
Alexander Figueroa.
That last name? F-I-G-U-R-A?
U-E-R.
U-E-R. Yeah, I got you. Okay. Figure. This is figure. I'm sorry. So Q minus W equals delta U. That's always correct for these three cycles, for all of them. So you have here either Q or W, Q or W, Q or W, Q or W. For example, here, what you have? Q or W? We have what?
Q.
Q. No, we have W. This is compression. How about heat addition? We have heat. What do you mean?
Q.
And we don't have W, or we have W, but it can be constant due to constant pressure. And expansion, do we have what? W or Q?
W.
W. How about the heat addition or heat rejection?
Q.
Q.
Q. We call it Q high and Q low. Always. Let's draw the cycle. Guys, somebody tell me from where to start in the TS diagram. Bottom left, bottom right. PV diagram. Bottom left or bottom right?
Bottom left.
Nope, bottom right. Because usually we compress. So we need to give room. This is one. This is PV diagram. Bottom right, because we're gonna compress. Pressure will build up and the volume will decrease. Usually. Okay? If it's expansion, go to the left, you are right. But usually we start for all the cycles from bottom left, bottom right. So we have first compression. Here, this compression, everything is reversible. Everything is reversible. Compression, heat addition, expansion, all of them are reversible. It means the most ideal process. I can reverse it without changing the surrounding. This is called reversible. Now, this is reversible and adiabatic. Reversible and adiabatic. So when you hear the word reversible and adiabatic, it means reversible and adiabatic. It means what, guys?
Isentropic.
Perfect. What's your name?
Christian.
Spell it.
C-H-R-I-S-T-I-A-N.
No. Guys, I'm slow. I'm old man. C-H-I.
C-H-R-I-S-T-I-A-N.
This is the last name?
That's the
Oh,
first name.
Christian. Okay.
Last name U-L-L.
Yula. Okay, I got you. I know you. Okay. So here we have PV diagram. We have compression, reversible, adiabatic, reversible, adiabatic, all of them. So it means reversible, adiabatic, reverse, isentropic. So for all these cases, including the Brighton and Rankine, we have isentropic compression and expansion. So here we have 1 to 2. Here, this is compression, which is isentropic. So here, Otto cycle, we assume the heat addition at constant. Heat addition at constant. Hello? For Otto cycle, Heat addition at constant what? Pressure?
Constant volume.
Constant volume. What's your name?
Jorge.
Spell it, please.
Jorge.
Jorge.
Yeah.
Okay. This is last name?
Rodriguez.
I think I know you. So let's keep it like this. Okay. So yes, that's correct. Here, stay with me. This is constant volume, correct? So heat addition at constant volume. How about here? How about diesel? Hello, hello.
The same constant volume.
Nope.
Constant pressure.
Yes. Who is this?
Anthony Mongan, Mongan.
This is last name?
Yeah,
Okay.
Mongan.
So this is constant pressure. So here, if you want to plot it, it's 1, 2, 2, 3. So it's horizontal. Here is vertical because volume is constant. Here is horizontal because pressure is constant in diesel. Exactly same process. Everything else is the same. Everything else is the same. It means expansion is what? Isentropic. Expansion what? Isentropic. Heat rejection at constant volume. So here is isentropic, isentropic. Finally, this is heat rejection. Finally, rejection. So for all these cases, we have all of them, including Brighton and Rankine. We have compression, isentropic, expansion, isentropic, heat rejection. For these three, the heat rejection at constant volume. Even this one, including this one. So 1, 2, 3, 4. So we still the heat rejection at constant volume. The heat, the compression and the expansion are isentropic. So here in the table we have two heat additions. Let's say this X, one here, one there. QH1 and QH2. The net heat is the addition of those two. So part of the heat added at constant volume, like the final, and part of the heat is added at constant. I think the final maybe diesel or devil, I don't remember. So I think one of these. Okay, so we have here R and R and RC and R and RC in both. Okay, and maybe information about X. Here we need 4. We need 4, we need 5. R is compression ratio, V1 over V2. Bigger volume over minimum volume. V1 is the biggest volume. V2 is the minimum volume. Actually, V1 equal V4 and V2 equal V3. RC is V3. RC is V3 over V2. It's still greater than 1, but much lower than R. Cutoff ratio. V3 over V2. Here, V3 over V2 is 1, but here is not. So we have 2 ratio in diesel, 1 ratio in O2, and 2 ratios and extra information. That X. We need to have information about this and this and this. We need 3 extra things. We need 2 things here, R and RC. We need 1 thing here, which is R. We can get the thermal efficiency, for example. For all of them, it's a piston cylinder going up and down. All of them 4 strokes, but we simplify for 2 strokes. We assume they are closed, and we have everything at air standard. Why air? Because the air to fuel ratio is so high. Air to fuel ratio, like for example 12, 20, so large, we can assume it's pure air. So the fuel doesn't change much of the composition of this. Imagine you have $100 and you just lost $5 or $6. It's nothing compared to the rest of the $100. So this is a 5% fuel. 20 means less than 5%, about 5% fuel, and 80%, 95% is air. Let's go to the TS diagram. Guys, TS diagram, we started from where? Bottom right or bottom left?
Bottom right. I mean bottom left.
It is bottom left, yeah.
Bottom
What's your
left.
name?
Thani.
Spell it.
Thani.
T
Hani.
Thi. I know you. Okay. So we will start always from bottom left. So tell me, Thani, for compression, how can I move here? Horizontally or slanted? How can I move from 1 to 2?
You go up.
What?
Horizontal
Nope.
or
It's-
vertical? Vertical.
Why?
Because give me a sec.
I'm cheating. Somebody is telling you something. Just kidding. So reversible adiabatic, that's why it's isentropic. A reversible adiabatic, that's why it's isentropic. Isentropic compression, isentropic expansion. Isentropic compression, isentropic expansion, always. So here we move vertically, okay? Kitani?
Okay.
So how about 2 to 3 heat addition? For O2, heat addition is what? At constant what?
Temperature.
Temperature.
No, it's constant volume. Constant pressure, constant volume. These are volume and pressure. This is the 3 cycles we are talking about here, 9.4, 5, and 6. Even, I think 9, 4, and 5, 4, and 6. So in chapter 9.4, 5, and 6, we have Otto cycle, diesel cycle, Lewis cycle, which is constant volume here. So this is vertical, which is here like this. This is always correct, guys. It means every time you have case diagram, this is the way you plot the constant volume line. This is every time you plot isentropic, it's like this. Always in the PV diagram, anywhere, any other chart. Constant volume, always like this in the PV diagram. Constant pressure, always like this in the PV diagram, horizontal. Isentropic, always vertical in the histogram. Okay? How about 3 to 4? 3 to 4, always what? Always what here for these 3 cases? 3 to 4, always what?
Reversible adiabatic.
Exactly, which means?
Constant entropy.
Exactly, which means isentropic. 4 to 1 is constant volume. What's your name?
Yihal, Y-I-H-A-L.
Say it again?
Y-I-H-A-L.
Okay, so let's summarize. And the same for this guy. Everything is the same, except this is pressure constant. Here, some pressure constant, or actually volume constant first, then pressure constant. Okay, this is the 4 cycles. Does it make sense, guys, for you? And we can predict the thermal efficiency, which is 1 minus 1 over R to the K minus 1. 1 here is complicated with R and RC, including K. We need K, of course. And the same for this guy. Okay, guys, let's take a 5-minute break. This chart for all of them, so you can get the thermal efficiency for every one of them. The same for the TS diagram. Now, let's go to 9.8 and chapter 10, which is Brighton and Rankine. Brighton is still gas cycle, it's still air standard cycle. Rankine is not. Rankine is the only one is steam. We use a steam table. Unlike those, Brighton is like jet engine. It has different components. It's not like piston cylinder. It is compressor, combustion chamber, and you have turbine. So we still have compression, heat addition, expansion, and heat rejection. So the same process. We have 1, 2, 3, 4, and go back to 1. So on. This is cycle. So the PV diagram again, compression and expansion always isentropic. Turbine. The compression and expansion always isentropic. So this is a PV diagram. exactly same as O2, but instead of having heat addition and heat rejection at constant volume, we have them at constant pressure. So we have something like this. 1, 2, 3, 4. Heat addition at constant pressure, heat rejection at constant pressure. So the only difference is heat addition and in terms of chart, heat addition and heat rejection at constant pressure. This is dump in the ambient pressure. I like TS diagram more for these cases. Very similar like this, but here pressure constant, pressure constant. Here 1, 2, compression, 3, 4. Guys, can somebody tell me what is the idea of this cycle? What is the idea? How they think about building this cycle to reduce work? What is the idea? The pressure lines are?
They're diverging.
Exactly. Who is this?
David Garcia.
David Garcia. Okay, gotcha. So this is exactly the same concept to everything. The volume lines diverging, the pressure line diverging. So in Brayton cycle, in jet engine, how we create thrust for an airplane, this is exactly the topic. All the pressure lines diverging and blower converging. That's why we pay less in compressor and get more in turbine by paying some heat. That's why if you compress and expand, you get nothing. Go vertically and downward. That doesn't give anything. And if it's even real, not ideal, it's even worse because you're gonna go slanted. So you're gonna get less, much less when you pay it for. So what happened? You need to compress, burn, expand, reject. Compress, burn. Always burning here at constant something. For engines like this, constant pressure, constant volume, constant pressure, constant volume, and constant pressure. They will engine. Again, the components here, which is open system, unlike there. So here we use Q minus W equal what? Equal what, guys? For open cycle. Neglecting kinetic energy and potential energy.
Change in H.
What?
Change in H.
Delta H. Exactly. This is exactly the change in enthalpy give you the change in the work or heat. What's your name?
Simon Vergara.
Spell the first name. Spell last name.
Vergara.
B-E-R. B-E-R.
Gara.
Yeah, I know. Okay. So either you have Q or W. Again, usually Q does not exist in compression and expansion because it's adiabatic. Always isentropic because it's reversible, adiabatic, reversible, adiabatic. But heat addition, it's called heat addition. Or heat addition, of course, it has entropy. And usually, if you had addition, entropy increases. Entropy increases. Heat rejection, entropy decreases, and so on. This is definition, thermodynamics definition or basics. So heat addition and rejection, of course, this is not isentropic. But compression and expansion, always adiabatic. Always, everything is reversible. It's always here isentropic and here isentropic. Always you will see them vertically in the TS diagram, vertically. All of them. Even in Rankine. Rankine, we have pump, we have boiler, we have turbine, we have condenser, and we go back. So we have boiler, again, 1, 2, 3, 4, and go back to 1. This is turbine. This is called steam turbine or power plant, Rankine cycle. Rankine cycle, very similar to Brayton cycle. The only difference is we talk about steam. So we need to plot the steam chart. We start like here, let's say here, and we compress. If it's TS diagram, this is PV diagram. Usually even it's PV, constant volume. Then we have another constant pressure line. again, pressure lines are diverging. That's why you have here 2. You have here constant pressure. Let's say this is 3, this is 4, this is 1. So this is a cycle. You have 2 constant pressure lines. So pressure is constant, 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 pressure is constant. Okay, guys? Okay? Always don't forget to write in non-vertical horizontal lines isentropic or pressure constant. So here I don't need to write a vertical lines or horizontals. But this one I need to write isentropic, 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 isentropic. Volume constant, pressure constant, volume constant, pressure constant, volume constant. Here, isentropic, isentropic, pressure constant, the same is here. If you plot in TS diagram, I like more TS diagram in these cycles. So very similar, but we're gonna actually, this is not correct. This is not correct. I'm sorry, this is not correct. It's maybe like this, something like this. Slanted. Here is vertical because here is not constant volume, but here is it is. So if you plot here, it's constant pressure line. Here is vertical, of course, because it's isentropic expansion. Of course, the turbine, it has isentropic expansion. Delta S is 0, of course, but it's not constant volume. It's slanted like this. It has some slope. Okay? The entropy increases. Actually decreases. It may be like this. It's something like that. Because entropy may remain the same. This is a constant entropy line in the V diagram, but this is a constant entropy line in TS diagram. I like more the TS diagram for these charts, for these cases. Because isentropic, just vertical lines, vertical line, vertical line. Compression, expansion, compression, expansion, compression, expansion, or power. Expansion means power. So here we have closed cycle, Q minus W equals delta U. Open cycle, Q minus W equals delta H. Here, delta U is CV delta T, unless diesel at constant pressure, because we have work, it's Q equals delta H. Here, everything, either this or this. Work, like compression, expansion, you have this. Heat addition, you have this. This always, yes? Yes? Hello? You have a question? For Brighton, which is gas, the same as others, this is CP delta T. If you have mass, both mass. I mean in extensive property, not intensive one. But for Rankine, no, we care about in H. We care about enthalpy. We care about temperature. We care about temperature. We care about temperature. Whenever you have cycle, make sure at every state you have temperature. For all of this cycle, except Dewel, you need to have 4 information. For example, P1, T1, let's say V2, and T3. That's it. You have 4 information. For Otto, diesel, Dewel, but plus 1. Brighton, rank. If you have 4 information, let's say P1, T1, V2, let's say T3, for example, or B2, anything, any 4 information like this, you can get everything in a cycle. Everything in a cycle. From 4 values. State 1, and 1 information is state 2, 1 information is state 3. That's it. Or at least link. Sometimes I don't need to give you Q3. I can give you heat. Q high or Q low. I don't need to give you T3 explicitly. I can give you something else to calculate T3. Usually I don't give you, for example, B2. I give you RP. Like pressure issue, B2 over P1. The same here, RP, which is pressure issue. The only special case of all of this is the pump. Pump, W is equal to, somebody tell me what the pump work is as a special case for a reversible pump. Pump, somebody tell me, new guys.
Isn't it negative V delta P?
Who's this?
Lisbeth, I already had answered.
I know, but I told new guys. So for everyone, guys, it's a V delta P. V delta P. P2 minus P1. We don't need enthalpy change in enthalpy here. Why? Pump is a device that compresses liquid. Incompressible liquid means a specific volume does not change. That's a good advantage. We can use the reversible work equation, which is W equal VdP, to get this. This is only happen for open system, steady, and reversible. Open system, steady, and reversible. This is go back to chapter 7.
Professor, I have a question.
Go ahead.
When we're finding the thermal efficiencies in terms of R, is that considered for ideal cases?
Yeah, usually these problems we assume reversible, so they are all ideals, like not T over T, but it is reversible. Okay, the most ideal one, the most efficient is Carnot, which is isothermal. Like we have compression and expansion isothermal cases, not isentropic. Okay. They are ideal, but not the most efficient. Okay. You cannot say 1 minus T3 over T1, for example. It's not gonna work. Or opposite, 1 minus T1 over T3. That's your question?
Yes, thank you.
No, it's not like that. This is not Carnot. Carnot should be Carnot. This is, yes, reversible, but not the most ideal. Okay. Now we have actually additional stuff, like for example, for Brighton, we define other things to improve the efficiency, like reheating, regeneration, and intercooling. If we have cooling for the compressor, regeneration of the turbine, and reheating from turbine to compressor. Some of the dumped heat to be used for heat after the compressor. For Rankine, actually for all of them, to improve the efficiency, just increasing T high, decreasing T low, always improve the efficiency, which is according to the Carnot cycle. Actually, this is a good example. You know, if you have a cold atmosphere, your car efficiency will be much better. That's why you see, for example, you do not go much to the mechanic if you are in the winter. You do not go to the mechanic. Yeah, that is real. And you have more efficient fuel. You burn less because delta T now is bigger because you have negative temperature outside. So your engine is more efficient. You pay less because T low is decreasing. That's why it's more efficient to operate at lower temperature. But if the atmosphere the ambient is hot, that's so bad. The computer will be inefficient. The car will be inefficient. Any device will be inefficient in high temperature atmosphere, which is T low is high. It's higher than supposed to be. So the higher TH is, the lower T lower is, the better efficiency you always have. Always, for all the designs. Otto, Diesel, Dewar, Ericsson, Brighton, Rankine, or any other cycles you have. Okay, guys? I wish that helps you to understand the cycles, which is the most excited part in the course. Let's go ahead now and solve the exam. Okay, guys? Okay?
Sounds good.
Okay. Please open the exam with me. Hopefully today I will post this review and lecture 17. So we'll be on the same page. I already posted the sample final exam model answer. It's online available, as I said in my announcement. So let's share now my screen and talk with you out loud. So can you see the exam, guys? So the same thing we have.
Yeah.
This is the last year, which is on the same day as yours. It was closed book. It was 2 hours, 10 problems. For you, it's 3 hours. 14, actually 15 problems. 15 problems. You have cheating sheet in the beginning. All the equations you need. You maybe not need anything else for the rest. Yeah. Question 1 was typically the same question as every exam as yours, which is give me some definition, true or false, what the value, just give me this. So what the thermodynamics is, if you have No heat engine can exchange heat for reservoir produce its Kelvin blank, and no device. So this kind of things you can read by yourself. The most important one, I think this one, I think in general, I mean, how we transfer energy into our system through heat, work, and mass flow. These are the three ways. This is the most important in terms of physics, not in the exam. I mean, in terms of physics. You know how to do it for refrigerator or heat pump or heat engine, like power plant, how to draw the Venn diagram and find the real and ideal COPs here. Maybe efficiency for power plant or heat engine. Maybe COPs for heat pump. So you need to know all of them. And of course, you need to have this question is important also, how to plot the TS or PV diagram. So here you have TS and PV. So both of them are here. So if you have any question, you have here. So how to plot the constant pressure line or lines, constant entropy or entropies, isentropic lines. So make sure you have the same value. For example, if you notice here, this line, can you see the 16.7? This line passing through this point, 1.67. This one, you see this guy? It passes through the same point. 0.6 passing this point. So at pressure 300, you will see the VG was 0.6. That's why it touches this point. The same here. I need to see this in the chart. If you notice also the S equal 7.354, guys, are you following me? S equals 7.35. It's exactly equal SG at P equal 101. So usually this point and this point are important. Usually the saturated vapor line, but also the saturated liquid line is important. You need to see whether it's here or there. So if it's TS, vertical. If it is PV, it's slanted like this. Okay? Isentropic line, constant entropy line in the PV diagram. Constant volume line is vertical, just vertical lines. The pressure lines are horizontals. Temperature line are like this. This is constant temperature line. Constant temperature line like this. Here is more clear. This is the exam. This is additional for you to know what's going on. So we have 2 lines, 3 regions, 1 point. Subcooled, saturated mixture, superheated. Everything here is superheated, like air. This is the actual happening in the air. Now, this is a saturated mixture. We have some vapor and some liquid with quality X. How much vapor mass to the total mass. And compressed liquid, which is pure liquid, but at lower temperature than the critical or transition temperature. And this is the critical point. 3 regions, 2 lines, 1 point. Okay, guys? So make sure that you know how to follow this. This problem typical to problem number 2 or 3 in the midterm 1, but a little bit more details. So I apply the force balance. This pressure is upward, this pressure downward, upward. It's always normal to the piston. So this is upward. F3 upward, F4 downward, F2 downward, F1 and F4 in the whole area, but 2 and 3 are annulus. For example, if you want the area here, it's D2 minus D1 squared, D2 squared minus D1 squared, D2 squared minus D2 squared. The same for area 2. It's D1 squared minus D2 squared. And of course, by over 4. I give you diameter ratio, divide by pi over 4 D1 squared. You will see everything is simplified like this. So you can get just one simple equation in all the pressures. And area ratios or diameter ratios square. So you can get just P1 in terms of the rest. Substitute by the pressures, you get P1. You can convert it by anything he wants. He wanted in PSI, convert it from Pascal to PSI. Is it hard, guys? Is it hard?
Easy.
You will see it in the exam. Okay? The same for this problem. So this problem, we have different version of this. So guys, this is a very important thing. If you copy paste from the model answer, you will get 0 because the equation is different, the setup is different, the numbers are different. Let's say you said, oh, okay, he's not gonna focus on number. No, I don't focus on number if they are wrong. but I will focus number if they are copied. This is a big difference. So if you copy it from your friend, if you copy it from the model answer, it means you did not read the question. So why you give you points? If you did a calculation and you make a mistake or 2 or 3, it's okay. I give you the full grade or a little bit decreased. So in intention mistake, it's okay. I can know for course. If I give you temperature here 20 degrees and you used, and in the exam was 40, don't use 20, use the 40, correct? If you use 20, it means you copied. It means 0. It means 0. You did nothing. You just copy paste. It means 0 for me. Okay, guys, make sense? Is it fair? So do not blindly copy. Please read and take data from problem. Ignore all the solutions. Ignore them. You already studied. You did all the mistakes in them. Now apply them. So you'll see the similar problem of this one, but a little bit different. So you have Q high, heat engine, Q low, and you have here heat pump. Heat pump is opposite, exactly opposite. Here in, out. This is out, in, like heat pump, and this is heat engine. Totally different in terms of design. But the connection is, the work is the same. You need one information, just one information. Here I give you a total waste. Sometimes I give you Q high, sometimes I give you something else. So you need to focus in the problem. You need to focus in the, read what's given. Sometimes they are the same, but different numbers. But also stick to your problem. Do not use other numbers. This problem, to plot the intercooling and regeneration, I may ask the same thing. To plot TS, PV, need to focus. Do not copy paste. Sometimes I ask for something else. For example, here I ask for intercooling regeneration. If I ask for something else and use intercooling, you're gonna get 0. If asking for intercooling and asking you to plot PV instead of TS, you need to plot PV, not TS. So you need to focus what is required. Is it TS, PV? Is it make sense, guys, for you? To when I ask you for something and you answer something else, I give you 0? You need to have focus, especially if copying. You need to focus what I asked you for. Mistake, it's okay, I will accept it. Here, this is good. Let's solve this one together. It's a Rankine cycle. Rankine cycle, it's pump, boiler, turbine, condenser. This is exactly what happened in reality. Actually, we are building here a greenhouse. We have the same thing, the same component. We have pump, we have 2 pressure lines. We are focusing to make it more efficient. So we have the same, almost the same thing. So we have ideal Rankine cycle. Very similar component. We have the power. It means I have W net, which is this 3 to 4 minus 2. Can you see this, guys? 3 to 4 minus 2. It was operating the steam air into the turbine at 10 megapascal and 500 Celsius. So I give you stage 3, completely stage 3, P3 and T3. Can you see this? P3 given and T3, which is a superheated vapor. This temperature is so high and this pressure is so low. It means you have superheated, table A6. This is water. The condenser exit pressure 10 kilopascal. So the P1 and P4 are 10 kilopascal because they are always constant pressure lines. This is constant pressure line, the same as what you see in the board. Pressure 1 equal P4, pressure 2 equal P3. Show the TS diagram. I can ask for the show PV diagram, something else, but very similar with respect to saturation lines. Yes, this is the saturation lines and this is the PV diagram. Determine the quality at the turbine exit here. Give me X4. Thermal efficiency, 1 minus Q low over Q high. The mass flow rate, because he gives you the power, and you can get the power per unit mass, you can get the mass. Let's go step by step. In state 1, you have just a pressure. And it is saturated liquid. You can get T1, which is saturated temperature, and you get H1, you can get everything at 1. So always these cases, we start at this point, complete liquid at saturated line. So we have P1. From table A5, you can get T1. From table A5, you can get T1. Saturated temperature at this pressure, 10 kilopascal. It is the same as state 4. State 4 can be here, state 4 can be here. But he said find the quality. It means it is here, saturated mixture. So state 1 is totally defined. I can get anything. The most important thing here is H's. Always box the H's. Also, at state 1, we can get V1, which is the same as V2. So we can get V1, which is the same as V2. Okay? Okay, guys? Hello?
Yeah.
Stage 3, you have P3 and T3. You can get easily H3. You can easily get S3, S3. Yes, from table what? Can somebody tell me what table? Point 3, stage 3. Stage 3, guys, from what table? Are you following me, guys? What table is stage 3? Hey, guys.
A6.
A6. Perfect. What's your name?
It's decent, but yeah, I'm sorry.
No worries. So we said at stage 3, because superheated and vapor, A4 for input temperature, salinity mixture, A5 salinity mixture for pressure input, A6 for superheated. So at this pressure and this temperature, you can get H3, S3, and so on. S3 was 6.59. It's the same S as 4. Why? Because this is turbine, isotropic expansion. You have the steps. This is open book. You have all the steps from T3 to 4. S3 equals C4. And you have pressure 4. So you can easily can get X4 because you have SG and SF. You can get X here. Okay, guys? Also, you can get H4, which is HF plus X H4. Once you get H4 and you have H3, you can get the work done here. Okay? And you can get everything here. Okay, let's back to 2. 1 to 2. At 2, we have W pump equal VDP. Because you have the compression ratio, you have P2, which is P3, and you have P4, which is P1. You can get the work. And it is H2, H1. You have H1. Remember, you have H1. You have P1. You have P2. You have V1. You can get easily H2. You can easily get H2. And W pump if you want it as well, because we want it. So again, you have V1 from state 1. State 1 is defined. P1, T1, H1, and V1. State 2, we just have P2. This equation. We can get W pump, which is VDP. You can get it. And H1 equals H2 and H1. We have H1, and we have all of them. You can get H2. Because we don't have table for this point in compressed liquid. If we have table, you can go ahead, get it. Because S1 equal S2. You can get everything at 2, but we don't have a complete table. That's why we get H2. We need only H. Why? Because the heat addition from 2 to 3, we need H2 and H3. Then we get H2 and we have H3. That's it. Stage 3 is defined. We can get H3 and S3 give to S4 because isentropic. You can get X4, the first required. The quality at 4, which is compressed liquid, but we don't have much information. That's why we use the work VDP, and we get H2 from this, and that's it. What we need, and always do that in the exam. We will do the same thing. In the exam, we'll do the same thing. From state 1 and VDP, you can get H2. Then at state 3 is completely defined. State 4 is completely defined. Just use S3, give it to S4 to get X4. S minus SF over FSV at P1 equal P4 equal 10 kilopascal. So you can get X4, you can get H4. Once you have all the H's, you are done. You have H1, 2, 3, 4, you are done. If you want thermal efficiency, W net over Q. W net is given. And Q high is also can be calculated from H3 and H2. So you can get the thermal efficiency. And also you can get the mass flow rate, which is W net over W per unit mass, which is H3 minus H4. You can get a minus actually bomb, but bomb is so small. It's so small compared to the 210 megawatt. It can be neglected, but you need to subtract it better. It's better to subtract. Problem number 7. It's a very good problem. Similar but not the same to our final. It's a special cycle. We discussed Otto, Diesel, Dewey, Brighton, and Rankine. But now we are discussing special cycle. So I give you the steps from 1 to 4. What happened? It says from 1 to 4, isobaric compression. 2 to 3, isochoric addition. Isentropic expansion. Finally, isochoric. This is isochoric, not isobaric. So this guy is exactly same as Otto. That's why here we need to say Otto cycle. So this is what exactly like Otto. Sometimes it's not the same. If I say this is constant pressure, it's diesel. So what happened here? I see ask it for PV and TS diagram. This is the PV. This is the S. Bottom left, bottom right, bottom left. 1, 2, 3, 4, 1. Isentropic, compression and expansion. 1, 2, 3, 4. This is called isentropic, compression and expansion. While everything else is isochoric. Hey guys, are you following me?
Mm-hmm.
So the first requirement is so easy. Just follow this, read. Compression from this. So I give you 4 information. P1, T1, P2. Then I give you here, I think T2, but it's behind this. So you can get the rest of the information. So you have P1, T1, you have P2, you have T3, I guess. From T3, which is 1500 Kelvin, you can get everything from these 4 only. You need here everywhere. What you need, guys? Somebody tell me what you want. Do you need enthalpy? What do you need, guys, here at every state?
H.
Nope. We need here, this is gas. We need, yes, it's H, but we need better T. T is better because it's U and H at the same time. CV delta T, CP delta T. Okay? So temperature, we need to make sure we have temperature everywhere. Here, you need H's, yes. You need H1, H2, H3, H4, yes. Rankine, you need H's. But all air gases, all of them, including the special cycle, including Carnot cycle, we need temperatures. Temperature always better. So I need to always, you see, box this temperature, which is the best thing for you. T3 is given already. So you have this. Once you have all the temperatures with the isentropic, ideal gas plus something. So here you have ideal gas, P1, you can get V1. From 1 to 2, isentropic, apply isentropic relation. You have P2, you have T1, P1, you can get T2 through isentropic relation, like this. You can get to T2. T2 and B2, you can get V2, ideal gas law. Ideal gas law. Always ideal gas law plus something. Here, at 3, you have T3, yes. You have constant volume. So get V2, give it to V3. Perfect. So from T3 and V3, you can get P3, ideal gas law, or ideal gas law, constant. Sometimes, if in the problem, I give you CP and CV. So you need to subtract to get R. Write this down, guys. If I give you CP and CV in a problem, you need to subtract to get R. Divide to get K. K is CP over CV. Do not use any K. Use my K, the one I gave you. So you will see, for example, in the final, I give you certain K. Use it. I give you certain CP and CV. Use them to get R and K. So you see, I say it, but some of you will not do it. In the exam, I will give you CP and CV. Use them to get K and R. Gas constant, specific heat ratio. Once you get T3 and V3, V3 was V2 because as isochoric, you get P3 from ideal gas law. State 4, you have the same volume from state 1, so you have V4. You have the same, actually, as the isentropic, so you can apply isentropic between 3 and 4. You have V3, you have V4, you have T3, you can get T4. If you want B4, ideal gas law. Now you can get everything. So calculate the network. Network is easy. Q high minus Q low. So you have here Q high and Q low. CV delta T, CV delta T. The difference between them is W net. Or here, work expansion minus work compression. So W here, CV delta T minus W here, CV delta T. Why CV, guys? Because this is closed system. Q minus W equals delta U. At the expansion, Q is 0, but W equals delta U. The same here, W equals delta U, which is CV delta T for closed system. So you can get Q high, you can get Q low, you can get W net. It's the second required. The third, similar efficiency, 1 minus Q high over Q, 1 minus Q high over Q low. And what this cycle is, it's an Otto cycle. This is how to get the entropy, which is we did it in review 3. Just we have delta S system and delta S surrounding. Because it's adiabatic, isolated, there is no heat going out or in the system, so there is no surrounding, only have system, which should be positive. And this is gas, just M. You remember CV ln T minus R ln P, or CV ln T plus R ln V ratio. So you can get delta S. Just you need to make sure you have all the temperature and pressures. And you have mass flow rate, you have the C heat capacity of the CE2, which can be obtained from table A2A, unless otherwise I mentioned. You have all the information, P1, T1, B1, and so on. So you can get delta S generation, which is the same as delta S system because it's uninsulated. Okay. The only thing here, to order to get the one of the information is using mass flow rate, m dot rho AV equal rho AV, and we have ideal gas P over RT to get some information like pressure or something else. So this is the only thing. He give you mass flow rate somewhere here, mass flow rate, or he asked about mass flow rate. Oh, we need mass flow rate for this equation. Okay. We need mass flow rate. So that's why P over RT get euro EV. So you can get mass flow rate. So using this equation to get it kilojoule per second, Kelvin second, which is rate. It's supposed to be kilojoule per kilogram Kelvin, multiplied by mass flow rate, it became kilojoule per Kelvin second. The same thing, but for helium gas compressed. I think these problems are easy. You can go it yourself. I need to go. Yeah, this one is good. This is Brighton cycle. Brighton cycle. It's aircraft engine. An aircraft engine, Brighton cycle. It's a pressure ratio. This is so important. P2 over P1. P2 over P1. I like the TS diagram. P2 over P1. Compression, heat addition, expansion, heat rejection. Compression from 1 to 2. Heat addition from 2 to 3. Expansion in the turbine and the pressure line are diverging. You need to make it a little bit diverging better than me. And 4 to 1 heat rejection. Again, isentropic, constant pressure heat addition, isentropic, constant pressure heat rejection. So you need to make sure at every state you need to have 2 information. You must make sure that you have temperature, at least temperature. These in red are important. He give you the inlet, which is 0 and 70, I think. Yeah, here, same as the final. So you have 0 Celsius and you have P1. And he compressed, so you have P2. And you already have isentropic, so you can get easily T2 or V2 from ideal gas load later. 2 to 3, you have constant pressure. So P2 is the same as P3. And he give you the heat added. This heat added related between T3 and T4. So Q high, which is MC delta T, you have mass flow rate. It was here 1. It can be different in the exam. You have CP, which is air, 1.005 from table A to A. You have T3, which you don't know, and you have T2, which you got it from isentropic relation between 1 and 2. You can get T3. Once you have T3 and B3, state 3 is defined. Apply isentropic between 3 and 4. 4, you know the P4, because pressure constant between 1 and 4. Isentropic between 3 and 4, you can get T4. Once you have all the temperature, 1, 2, 3, 4, everything is done. W net, W turbine minus W compressor. MEC delta T minus MEC delta T. compressor, a turbine, 3, 4, compressor, 1, 2. Remember, this is TS diagram. Or Q high minus Q low, MC delta T. Why MC? Why CB, guys, not CV? Can somebody tell me why CB, not CV? Different from Ethan? Why it's CP delta T, not CV?
Constant pressure.
Yeah, yes, but how about isentropic? I'm talking about isentropic. Constant pressure, yes, makes sense even for closed system. But why it's isentropic? Because it's open system. So everything here is open system. Unlike Otto, diesel, and Dewey cycles, they are closed cycles. So here 1 to 2, it's open system, isentropic. So we always have Q minus W equal delta H. Q minus W equal delta H across input and output now. Instead of 1 to 2 states, it's 1 and 2 input and output. So this is the input of compressor, this is output of compressor. This is the input of the turbine, exit of the turbine, and so on. So here you always have CP because it's delta H across the compressor. Yes, for heat addition and injection, you can say even for open system or closed system, you can say that because pressure is constant. But the main reason here was because it's open system, CP delta T. Okay, guys, make sense? Heat thermal, it's 1 minus Q over Q high. And there is a very good check for you here. You got Q high and Q low from the temperatures. That's very good check for you. Very, very important and good check for you. You can get heat thermal, yes. But you can check it. Because this is, everything is ideal. You can say 1 minus 1 over RP, K minus 1 over K. And you have RP, which is 10. Pressure ratio was 10. So you can directly get this number by saying 48.2%. Which is the same exactly as this one. Exactly. There is no error. Okay, guys? In the exam, if I did not ask for anything except thermal efficiency, you need to go through the steps. Some guy was so smart. I like his solution. He said, you want thermal efficiency and work and power. That's easy. He said that. He said this. I have thermal efficiency, correct? Correct? From RP. Correct, guys? He can get easily thermal efficiency. He said, I have the heat and thermal efficiency. I can get the power produced. The thermal efficiency, W net over Q high. And he solved it in 1 minute. Can you see that, guys? Last year, one of you, like Ethan, he said, oh, I'm going to solve this problem. I have RP. I can get thermal efficiency directly from this equation. Then I have either thermal, which is W net over Q high, and I have Q high. I can get W net, which is that's it. Hey guys, do you like it?
Yeah, man.
So sometimes you can save a lot of time. A lot of time. He's much smarter than me. I did not notice that. That's very good. I give him bonus actually in this point because he solved it in 1 minute, in even less than a minute. RP, efficiency, Q high, you get power. That's it. You don't need to go through all the steps. But in this exam, I will do something else to make it you go through all the steps. Sorry for that, guys. Okay? I will ask for something else. Okay? Usually, we are bad guys. We are bad professors. So here in this problem, I simply said, you are a professor, explain 2 points. So for example, I said, how about the compressibility factor? I give you an example for you. I explain for the compressibility factor. If you have pressure and temperature for gases, you can see how good you are or bad you are. The one, so I explain. If R or Z is closer to 1, you are very close to be an ideal gas, PV equal RT. The far you are from 1, the worse you are. So this is a very simple explanation of anything. I said, let's say you explain first law of thermodynamics, Q minus W equal delta U, and explain it. And do not repeat it. Then say first law of thermodynamics for open system. Don't say that. Don't repeat 2 things similar. Like for example, here I said, Do not explain a cycle or a process. I remember I give them the note. Do not repeat the same thing. So I give it to you in this exam. So for example, you're gonna say, entropy generation, delta S equal this. How can explain this? And explain it in a very simple words. You don't need to go much equation, just one equation, and simplify or explain what's going on. So the ideal gas law is a very powerful law. You can simply solve an engine without table. Just one simple equation and other equations like delta U, delta H, delta S for ideal gas. But first, make sure it's ideal gas. So you need to avoid the steam table. We can solve Brighton cycle, Otto cycle, anything without having tables. This is what extra credit, which is proof from this to this, and delta S from this to something else. I can ask you in the final, similar but not the same. Make sure you follow this. Guys, do you have any questions? Your final is 15 problem, 3 hours. They have 2 hours. It's some of the problem is straightforward, very straightforward, very similar to these problems, and the homeworks and the list, the pool I give you. Don't worry, it's from the pool. No way. Okay, guys. Any questions?
Yeah, just had a quick question. You said CP minus CV equals R, right?
Yes, of course. This is
Okay.
from chapter. Go back to chapter 3 when we discuss ideal gas law. We said CP over CV is K, specific heat ratio. CP minus CV is R, gas constant. That's the definition of R. If you don't remember, go back to chapter 3. I think lecture number 3 also. Okay, ideal gas law. Anything else, guys?
Yeah, for question 10, we explain any topic
Anything.
we want.
Anything. That's, you see how easy I am? Anything. Pick up anything you like in the course and explain it for me.
So we could just say, for an example, we could just do like the Pant diagram of like a refrigerant, of a refrigerant, and just
That's it.
Okay.
You know what? I've learned a lot of things. I'm sure that you understand second of thermodynamics because you plot Q high and Q low W net. You understand what's going on in the balance, which is Q high minus Q low equal to W net. You explain the cycle system, which is not violate the second of thermodynamics. You explain that's a very simple way. Explain it like anything. First of thermodynamics. It's the energy can be neither created or destroyed, but transformed from form to another. Q minus W delta U. So from heat, I can get delta U. From delta U, I can get heat, and so on. So you can explain it in a very primitive words, like very simple words. Okay, how this matter or and you understand this physics. That's it. Very simple. Like you read this, you'll see how simple it is. We have steam table. It's a lot of information. We can simplify it to be an equation. Like what? Ideal gas, and this is the equation. But we need to be closer to one. That's it. So simple. I just mentioned that. And don't worry, most of the students get 3 because they used a very simple, not repeated. Like don't say Otto cycle, Rankine cycle. I will give you one of them 0. Just use Otto cycle, entropy generation. First of thermodynamics, diesel cycle. I don't know, pick up any, like for example, CP, heat capacity. It's actually the integration of CP, delta H is CP delta T, or CP delta T. That's a very good assumption. Explain this assumption. Just assumption, simplification of enthalpy calculation for ideal gas. The same here. You can assume any topic, anything. You have 9, 10 chapters with a lot of details. You can pick up anything. Exergy, explain exergy. Irreversibility, Carnot cycle, any one of the cycles, but just one cycle. Do not repeat. Okay, make sense?